Hello everyone, let's continue on from the previous lesson. Now let's recap back in magnetism. We learned that North Pole and North Pole repel, South Pole and South Pole repel, North and South will attract. So that is very clear. Once you have the North and South polarity, it's very clear which will attract and which will repel. But when you look at the diagram here, what I have are two conductors carrying current. The one on the left is the current is flowing out of the plane, and the one on the right, the current is flowing into the plane. And using right hand grip rule, we are able to determine the direction of the magnetic field around each current. So this time around, what we are lacking is the north and south polarity to help us deduce whether there's attraction or repulsion. What we can only rely on are magnetic field lines. So by looking at this diagram, how do we know whether these two currents shown in this diagram here, whether the two wires will attract or repel? We first look at the direction of magnetic field lines. When we look at the direction of magnetic field lines, we are then able to deduce whether they will attract or repel. Now, first of all, let's look in between the two wires, and from there, we can deduce whether the magnetic strength becomes stronger or weaker. Now, if you look in between the wires, this is the direction of the magnetic field lines. The one on the left, the general direction is up. Now for the one on the right, the general direction is also upwards. So what happens when we take these two wires and push them closer together? When we push them closer together, what we are going to encounter is this diagram, where the magnetic field lines just come closer together. And in an earlier video, we say that when the magnetic field lines are closer together, the magnetic strength is actually stronger, right? So over here, we see that since the directions are all in the same direction, so when you push them closer, there's no cancellation. So the number of magnetic field lines increases. So we say number of magnetic field lines increases, and hence magnetic strength increases. Now, let's look at the other two regions. Okay, let's call this region A and let's call this region C. So we call the center region B. Now let's take a look at A and C. Right, for A and C, the magnetic field lines are further apart. Hence, magnetic strength is weaker. So the same goes for C. The magnetic field lines the magnetic field lines are further apart, and hence the magnetic strength is weaker. So from here, what we can deduce is that, okay, I'll choose a different ink. Magnetic strength at B is greater than magnetic strength at A and C. Therefore, the two wires repel. That's all. Right, so you see, first, we must know how to draw a magnetic field lines, and then we have to see where, when we put the two wires together, we have to see where the increase in the number of magnetic field lines is. Then from there, we deduce that the magnetic strength at B is greater than the magnetic strength at A and C, so the two wires will repel. Now, what happens if I have two wires carrying current, and both are flowing in the same direction, and in this diagram here, they are flowing out of the plane? So we go back to the very basics again. Let's take a look at the center in between the two current. Now, for the one on the left, the direction of the current is upwards. The direction of the magnetic field. But for the one on the right, you notice that the direction of magnetic field is down. So that means if I were to pull the two wires together, as shown in this diagram, I just put them in different colors for clearer distinction. Now, if I were to put them together, you realize that some of the lines are up, some of the lines are down. Right, so in a way, we can say that the magnetic field lines cancel each other. So if you're going to label the region A, B, C, in the region B, in the center between the two wires, the magnetic field lines cancel each other out. And what will be the resultant magnetic field lines? It will be this. I'm just going to draw a very rough one to show you how it's derived. Okay, so it will be like this. Right, so in a way, what's in the center here is cancelled out. Right, it's cancelled out. So the result is this. The result is this. And don't forget, I'm going to label the region A, B, C. Some magnetic field lines in the region B are cancelled out. Magnetic strength becomes weaker. For region A and C, there's no change in magnetic field lines, and region A, there's no change in magnetic field lines. Okay, so you see in the middle it became weaker, but at A and C there's no change. So because there's no change in magnetic field lines, no change in magnetic strength. No change in magnetic strength. So at the ends, no change in magnetic strength, but in the middle, the strength becomes weaker. Right, the strength becomes weaker, and therefore we say that magnetic strength at B is weaker than magnetic strength at A and C. Therefore, the two wires attract each other. So you see the forces at A and C are now stronger than the force at B. So the resultant force will be towards the center. Or should I say towards in between the two wires. So that sums up the interaction between the magnetic fields surrounding the current of two wires.